In this tutorial, we're going to be using Kangaroo to do some physics-based modeling. And the first example that I think is probably the most easiest to understand is to model a hanging chain, or inversely, a catenary curve. And the catenary curve is special because as kind of not inventor, but the mathematician and physicist behind this is Robert Hooke, probably most famous for Hooke's law, which has to do with springs and distances. But I believe, and I'm going to butcher this quote, but it's as hangs the flexible line, so inversely stands the rigid arch. And sorry if I butchered that. I'm doing this a little bit from memory here. But essentially what it gets at is that if you hang a line that's completely flexible, it will essentially remain completely within tension. And then if you were to flip that upside down, it would remain completely in compression. And as long as that compressional line remains within the depth of your arch, or your rigid stone arch, it'll stand up. Probably one of the most famous examples of this is Antoni Gaudi's work on the Sagrada Familia and his inverted chain hanging examples. Here we can see someone building one of these essentially as simply and as cheaply as possible. These are not by any means special bricks, but they are all standing up. There's very little, if any, mortar between these. From here, we are going to jump into Rhino, and we're going to come into Grasshopper. Make this a little bit bigger. I have a few different plugins added in, but we're going to be using Kangaroo2, which should be already installed in Grasshopper. And so we're going to start making a physics-based model, which is what Kangaroo is really good at. So I'm just going to initiate bifocals so that everyone can see both the icons and the names. So the way that I like to start when I'm building a physics-based model or a Kangaroo, I usually like to start with the engine. And there's a few different flavors of the engine. The first one is Bouncy Solver, which is my favorite because I like to see how the physics are reacting. And then the rest of these solvers, they kind of have their own flavor as well. If you're unsure, just use the main solver, just called solver. But for this example, we're going to use Bouncy Solver just so we can see what's happening. So once I drop that in, and I'll just put this directly under the main tab here so it makes a little bit more sense, is it's going to ask us for a series of inputs. And before I get into that, I would like just to talk about how this solver behaves. And essentially, it is a loop, or it will iterate over a series of inputs, in this case goals, to try to achieve an equilibrium or a balanced model. And so it's up to us to think about what it is we want to put in here to come up with these goals, and then to provide those goals with the necessary geometry. So I like to almost work backwards from my solver. Once you start using this and you become more familiar with Kangaroo, you can start with the geometry and then move the other direction. But for the sake of this example, I find it a little bit easier to start with kind of the node that's doing all of the work and then work backwards from that. So I'm going to open up Paint here just to explain how I'm going to do this. So by definition, a point will have a start and an end. We want to connect those two, and that makes a line, right? Forgive my terrible typing in Paint or lettering. And so if we want this to be flexible, we're going to have to break it into a series of segments so that we can make the segments kind of move, and we can keep our start and our end points if we care about those. But then we can have each of the segments move and flex our line a bit. And so this is going to be my base geometry that I'll start with, and I'll feed it a series, I'll feed this into my goals. And for example, my goals, if I want to make a catenary curve that's hanging down like this, I will want each of my points to be acted on by a force. In this case, let's call it gravity. It's pretty much a unitary force moving downward. But I also want the distances between each one of my segments here to have kind of a fixed length. I want these to not just be able to stretch into infinity. That's not the infinity symbol. I don't want these to stretch into infinity. I want them to be able to have a spring force. So if I think about these as springs, just to bring it back into Robert Hooke and the amazing work he did is describing our physical world. So with now that I have my sketch and I have my idea of how I want this to work, I can start working backwards. So if I go to my goals, I'm going to want, well, maybe I'll start with that geometry first. So I'm going to open up a perspective view. I think it's a little bit maybe easier to understand. And I'm going to need 2 points to define a line. So I will make a point container. And I can find this under the params tab and go to geometry and point, first one. And I'm going to copy this so that I have a start and an end point. And from here in Grasshopper, I can right click and I'll say set one point. And even though I don't have a Rhino point defined, Grasshopper will let me click in the Rhino canvas and define that. The nice thing about these is now I can move them a little bit around if I want to. I'm going to click on the second one and I'll say set one point. And I'll make another point over here. And now I'll need a line to connect them. So I'll go to, I can either go into curve and go into line 2 point, or I can just say line. And if I look up here, I say I have an option to create a line between 2 points. That's what I'll use. So I'll create a start and an end. And now, as we discussed in the sketch, this is a solid line in a way. it's a two-dimensional line, but it is not flexible. We don't have any areas where it could flex upon. So we will need to create those. Under curve and division, we can say divide curve. And this will allow us to break our curve up into a series of points. And if we wanted to, we could change this count number. Maybe we'll do that right now. I'm just going to type in the number 12 by double-clicking, typing a number, and it will automatically give me a number slider. And so now I can change the number of points within my curve or the number of flexible parts within my curve. And the next thing I want to do is get the segments. So if I look at this, really only thing it's giving me are points and parameters. So if I come back up under division and I go to shatter, I can shatter my initial line as a curve, and then I can feed the parameters of those points in, and it will give me a series of segments. So I have 16 segments and I have a count of 16 for my divisions. So that's exactly what I want. Then from here, I need to start defining some goals. And within these goals, I want gravity to be affecting all of the points or flexible segments of my curve, but I also want the endpoints to not move. And so if I go back into Kangaroo2 and I look at everything left of the main tab, and I think I started out with the solver underneath main, everything left of the main tab is referring to a goal. And we have different flavors of goals. There's goals for points, there's goals for meshes, there's goals for lines, there's collisions, and so on and so forth. Strongly recommend you kind of look through this, peruse around, see what types of goals that are out there, and I think it will open up what's possible. But for now, we're going to focus on just this catenary curve. So I need to make a point goal. And what I want to do is I want to anchor my endpoints to be the points that are creating my line. So I'm going to bring those in. If I hold shift, I can add multiple anchors. So I'm going to bring that over here. I'm going to call this little bit of blank space my goals section. Next, as discussed, I want to make sure that these lines can't just explode indefinitely. So if I go to my goals in lines, I can set a length. And this length line goal is very similar to a spring. So I can adjust it accordingly. And so for those lines, I want to bring in the segments that I have for each one of those. And so I can bring each of those into my goal objects. And as I have this selected, we can see that it's incorporating them all. In order to get this to work, there are two main things that I want to have, or three really. First is to have some goals that I want to achieve. The second, I want to have the ability to essentially have this recompute or restart. And the third is that I want to be able to turn it on. So for the reset, I like to use a button since I just want to fire off a true-false statement, and that's what it's looking for. If we hover over it, we can see that it's asking for a Boolean toggle. And I know that because if I hover over it, it says that the one locally defined value is false. So if I set that to true, it'll probably reset, and that's what my button is doing. If I look down underneath the solver, I can see it changing its status when I click that, which is great. And then I also want to turn it on. And to turn it on, what I need to do for this one, I like to use a Boolean toggle. Similarly, we can hover over on. We can see that the one locally defined value is set to true. So if I plug this in, we can see that it's paused, and I can turn it on, and I can turn it off. This will be very useful a little bit further down the line. And so I'm still not really seeing anything happen. And the reason for that is I'm missing the main ingredient. And if I'm thinking about this being a line hanging, I actually need to add a load into the equation of my goals. And so the load, or the areas that I want to load to be acted upon, are all of the little points in between my line. And then I want to add this into my goal objects. So then when I set the solver to true, I can see I get an arch. And I can click that a few times and I can see why it's called the bouncy solver. I can see how these iterations are working out. So if I move this over a little bit, I zoom in, I can see I'm getting my catenary arch. Now, if I wanted to up my count, this is going to break this because I'm essentially adding more geometry into my solver than it initially was thinking of. And that's okay. In extreme cases, this will crash your machine. But for this line, it'll work out fine. And so we will add some more points and we will confuse it. And this is where the button comes in handy over for our bouncy solver in our reset tab. And for our goals, we can hit reset. And now we can see we're getting all of those lines coming together. And we can start to see how this arch is playing out. With that, we have our goals, we have our solver, and we have some input geometry. And what I was hoping to do in this example was explain how all three of these work. But to go a little bit further, we can start to play with the strength and the length and the amount of force that's going into this. So let's say I want this force to go the other direction. Right now we have a force vector of 0, 0, 1. So I'm going to make a vector. And I can type in vector and I can go to vector x, y, z. Otherwise I can get there by going to the vector tab. And I'm going to make a vector x, y, z. And right now it is set to the default force vector set to 0, 0, 1. And so that essentially equates to 0 for the x, 0 for the y, and 1 for the z. So if I put in negative 1.0, and I'm going to use the alligator to set the other upper end, and I'll say 1.0, and I'll put that in here for the z component. I won't change the x or the y right now. I will leave those as zeros. And I will put in the vector into the force vector. We can see now that's going down. And the fun part is I can play with how this vector works. And so as I'm modeling, I kind of have a little bit of a playground here. This would be the equivalent of kind of like slapping a rubber band up and down maybe, but anyway, a pretty fun little thing to do. Now, because the computer doesn't know that gravity always goes down to the earth, we can actually give this whatever we want, which is kind of fun. So I'm going to plug in the same number slider for my y, and now we can see it's pulling down and in the negative y direction. But I could make this a positive y, and it'll pull it the other direction. So now my gravity is really moving wherever I want it to be. And I can even enter this in for the x as well. And we can see that now we're getting even a crazier, weird shape of all three of these playing together. And how that might start to affect how I'm designing this. Which is pretty cool, I think. Overall, a lot of fun to play with just as terms of a simple divided line. And with that, that's pretty much all it is for making a catenary curve in Kangaroo. There are a few other things I might add to this. Essentially, you provided the right geometry and you set up the goals. You're asking physics the right question to then get the right answer. If you don't configure these two properly, then your answer isn't going to be, it's going to be worth the amount of effort you put in, essentially. I want to go over making a shell, a catenary shell. And what I'm going to do is, because I'm in Grasshopper, I'm going to do this all in Grasshopper. I'm going to make a primitive mesh plane. And I have my boundary and my width count and my height count. And so for my boundary, I see that I have a rectangle as an input. I want to be able to change that. So I'm going to say rectangle. I can get to the rectangle by going to curve and primitive, and I have a rectangle down here. And so I want to be able to move this curve so that I can look at it better and I'm not in conflict with my catenary line here, I will make an XY plane, and I will move this over, and then I need an origin point, so I will make another point container. And then I will right click on this and I will set one point, and I'll bring that up here. I can bring that in for my origin. And then for my X size and my Y size, I'm going to make this quite a bit bigger. I might just type in 12 for now and see what that does. Great. Probably want this to be a little bit bigger. Then I'll just bring this in for both. I don't need two separate sliders for now. I'll make this maybe about the same width there. And then I can bring this rectangle into my boundary, and now I have my own custom mesh here. So after I have my mesh plane, I essentially want to be able to anchor the corners as a goal. And I might jump back into Paint for a second. So using Paint as the way to describe this, I will make a plane, and I want each of my corners to be anchored down. And then I want gravity to actually act upwards on this so that I can see the inverted chain. But I want it to act upon the entirety of my surface. So I want every little stitch and piece inside of my surface to also have gravity being affected on it. And that is where meshes will become very, very useful, because with a mesh, we can control how big each of the little parts and pieces are within it. And so we can start to build different meshes to behave in different ways so that we can get our desired results. I don't want to use this analogy, but essentially it's garbage in, garbage out. But I would maybe say the other way around. Maybe it's gold in, gold out. That seems a little bit more positive. So I have my mesh, and what I want to do is get the corners. And fortunately, in Kangaroo2, there is a mesh tab that has a whole bunch of useful features that we can use to get out some of our goals to build this. So I'm going to go, and the first thing that I'm going to be looking for is mesh corners, is right here. So I'm going to take my mesh, I'm going to get these mesh corners. And if I bring this over, I'm just going to make this a little bit easier to see while I'm working on it. Bring this over to the left side. We'll bring this up a little bit higher. So we can see we're getting all four of my mesh corners. So there, I want to make a goal with a point, and I'm going to make that an anchor. So here we are already in our goal areas. Very nice. The next thing I want is all of the points within my mesh to be acted upon by my unitary force. If we come into our goals point, I'm going to just pull this out because this is going to be the one acting on it, but I still have to extract all of those points from my mesh. The way that I'm going to do that is I'm going to come in again to my mesh tools. There's multiple ways to do this, but I prefer to use the option within Kangaroo, which is naked vertices. And this will get you all of the points within your mesh. And I will bring in my clothed, not my clothed index, my clothed points and my naked points, which are the lower two options within this. And I can see that I have a unitary force acting upon those. The next thing that I will want to do is to create a line or a spring force so that my fabric doesn't just rip apart into infinity and never have a state of equilibrium. It needs to not be able to stretch to a certain extent. So similar to our catenary curve, I can come into my line and I will get my line length. And now I have to get the lines of my mesh, which I can get by going over to Mesh Analysis and Mesh Edges. And we'll see this is very similar to getting the naked vertices, is that I have naked edges and I have interior edges. And I'm going to want both of those for my lines. So bring both of those in. Now we can see here we have a very similar goal stack. And let me just increase this a little bit, give everyone a little bit more reality to read what's going on. So I can come back into Kangaroo2 and I will get my bouncy solver. And from here, I can put in my goal objects. So I'm going to add in my line lengths. I'm going to add in the load. And as we can see, that just flew off into infinity because I have no anchors. And to kind of show that, I'll make my Boolean toggle for run. And I'm going to turn that off for now. And then I'll make my button for the reset the same way that we did for the curve example. And I will set this to true. And now when I click reset, we can just see that we have a whole bunch of lines just flying upwards. There's nothing stopping them. They're completely free to fly upwards. And that's because we do not have our anchors added in here. So if I add them, we can see that it just went flipping around and went all crazy on me. But if I hit reset, we can see we're getting our mesh starting to relax a bit. And we're getting a shape that is directly related to the mesh edges that we have internalized. To show how maybe this would work differently and maybe a little bit more random and organic, what we can do is triangulate that mesh. So we have our mesh plane, and I'm going to hold the Alt key and just slide this over for a little bit more room. Unfortunately, I grabbed my vector XYZ up here. I'll just bring them in. And what I want to do, if I come into my mesh tab, there is a triangulation tool. And what I can do is I can say try remesh for a triangular remesh. I'll bring in my geometry, and I now have a triangulated mesh up here. And you can see our vertices and our faces. We have 537 vertices and 992 faces comparatively to our 121 and 100. And so with this, we're going to be breaking our solver for a second. It's not going to be happy with me just replacing this stuff willy-nilly. And we're also going to be adding a ton of computing time because now we are making the solver have to account for a lot more different pieces. So I'll bring this into my mesh, and I'll bring this into my mesh. Now I pretty much have like a piece of cloth held up. And lastly, I will bring in my mesh corners, and I can click on reset. And now we can see we have a much more dense model, and we're getting a little bit different behavior, which is an interesting topic on its own. I'm not going to go too far into that, but if we think about this acting as a cloth, this triangulation actually is helping it behave a little bit more the way that it probably should. If I look at my kangaroo model, all I'm getting is the points and the lines, and I'm not actually seeing a mesh. I can see right through this. So if I want to be able to see the mesh, if I come into Kangaroo2, under main, there is a great tool called show. And what I'll do is I'll add this show from my mesh, from my triangulated mesh, into my goals. And now I get to see that. The other tool that I want to just reference in here is there is a grab tool. And if I add this in here, it will allow me to grab my mesh. And if I select one of these points, it'll let me kind of rip it around and pull it, which makes it pretty interesting because I can start to think about how a point load or a tent pole might act upon on the model. So a lot of fun to play around with. If you're a nerd like me, it's also a nice way to be able to understand your model a little bit more intuitively. If you're getting some crazy wind loads or something like that, I don't know. This feels like a jiggly piece of jello, but actually, if we think about it as a compressive or compressive structure, there is stuff to find from that. These different inputs will allow you to turn it on and off, so you don't have to be able to grab it, and also be able to change how hard you grab things and how far you can move them when you grab them. Lastly, I would just add is to be able to visualize this a little bit better. What I might do is just turn off all of my inputs. And then from my outputs, if I hover over them, I'll see that I have a mesh, and then I have a null, and then I have a whole bunch of lines. So if I just want to filter out certain elements, one is I can make a container for that, but we'll see that we're feeding in a whole list of items. It's not very happy about that. It is getting the mesh, but there's a whole bunch of null items for everything that wasn't a mesh within this list. So the other way to go about that is to list item. And I know that my 0 is my first object, which is my mesh. And then if I turn off my solver, I just have my shell here. I kind of like to see the lines. So we could go through and iterate through that as different lists and so on and so forth. But just wanted to show how these outputs work. Is that the output is first getting what I gave it to show, and then it's also trying to get as much geometry from our different goals as we put them in there. So this should conclude everything I want to go over with Kangaroo, and as an introduction, there are a lot of really great and fun elements to play around with, and that's where I suggest everyone goes through this. For like angle goals, for example, we could make, instead of making a hanging slack line, we could make a flexible kind of like a piece of steel, and so it will bend according, it'll try to resist that bending and give us some interesting curves. We have collision goals. There's a whole bunch of fun stuff. If everyone is trying to just barely make sense of Kangaroo in the beginning, I strongly recommend everyone visits Daniel Piker's GitHub. Daniel Piker is the individual who's founded Kangaroo as a plugin, is an amazing mathematician, engineer, and community member within Grasshopper. But to find his base examples, if you type in GitHub Kangaroo examples, and if that's not bringing it up, add Daniel Piker to that search query and you will find it. Dig down, you can download all of his example files. It's very open and it's a lot of fun to experiment with. So with that, I hope everyone found something useful. Let me know in the comments or otherwise if you want to see a specific tool or use example or physics problem or setup or system, or if you have problems and you need some help. Goodbye and good luck.